Hello, my name is Seth Holder, and this is my Physics 1 lab on constant velocity. We observed an object traveling at constant velocity and used Tracker to make note of its location at different times. Tracker is a website that allows us to place points at various locations at various times to record observations about our system. We were then able to take an average velocity by dividing its position by the time it took to travel to each of these positions. To find these measurements, we made a few key assumptions, such as there being no resistance, such as friction or air resistance. The object would travel in a continuous straight line, and we also assumed that the net force would be equal to zero, meaning that its speed would not change throughout the time it traveled. The tools that we used during our calculations are Newton's first and second laws, as well as the position and velocity update formula. Newton's first law states that an object in rest or motion will stay at rest or in motion unless acted upon by an outside force. This means that if we have a net force of zero, an object in motion will stay at the same motion throughout the course of its journey. Newton's second law says the change in motion of an object is proportional to the magnitude of the force applied. The force we applied will be the initial push we had when we started rolling our marker. We then also had the position and velocity update formula, which was used in our tracker calculations to find the marker at different times and to calculate the speed we needed throughout the whole journey of the marker. During this experiment, we used a marker as our system because of its circular shape. The circular shape was important so the friction would be a negligible factor and would not be a huge force pulling back on the marker. Other forces that will not be included in our calculations are air resistance and the initial force applied, as well as the direction of the marker after the force was applied. The marker might have twisted a little bit and its speed might be a little different because of its direction, but we will not be including that in our calculations. This is the video we used for our calculations. As you can see, we recorded the video, we put it in a tracker, and then we got a few key points at different locations during the video. This is the data we were able to gather after finding the key points during the video. We have time in seconds, which it took a total of 1.37 seconds to travel, a total of 0.6 meters. This is my GlowScript code, which was used to make the model of the marker's travel. I used the velocity calculation we made earlier as the average velocity and used the position update formula for the graph that was generated from the data. This gives us a straight continuous line with constant velocity. This is both the model and the graph that was generated from the data on the last slide. As you can see, in 1.37 seconds, it traveled slightly less than 0.6 meters. This is an image of both graphs together, both the one in Tracker and the one in GlowScript. The light gray is the one in GlowScript, as it did not travel the full 0.6 meters. However, it was more consistent than the one in Tracker, largely due to outside forces, which are just can be accounted to human error. Then have a what if question. What if the x-axis was flipped? The data would still look the same in this case. However, instead of resulting in a positive slope, it would yield a negative slope on the chart. This would be because the magnitude would still be the same, the rate of change would still be the same, but it would be negative as it'd be going in the negative x direction instead of the positive x direction. The results would be basically the same, but it would just appear as if the marker was moving backwards instead of forwards. What does this mean? Can you determine the net forces acting on the marker? No, not necessarily. In a computational model, it is possible to make the net force equal to zero. However, that means we will not be including air resistance, gravity, friction, and unlevel surfaces, which will act on the marker. And in a real situation, there's no way to prevent these outside forces from having some effect. They could cause a positive acceleration, which is unlikely, or they could cause a negative acceleration through like friction, which is more likely. The reality is that it's impossible to achieve constant motion outside of a computational model, as there will always be some force acting upon the object. Finally, we have to account for the error in our findings. This is in reality just human error, how it was applied to the marker, how it might not be fully in one direction, as well as the outside forces acting on it that were not taken into account when we made our calculation. There's also probably a few errors in the computational data, such as the coding, or maybe just how it was inputted into tracker. It could have been improperly calibrated, or some of the points could have been a little off, leading to the calculations being slightly different than they were in the realistic model.